some technical problems were detected, but starting from now we have the correct way of fixing the lecture. Okay. So now we reformulate the same definition. I would say it is an ugly one, and you saw that it needs some efforts to be reproduced. So we give the categorical definition of the same object. To do this, we start with a general construction. So for a partially ordered set, again I with the reflexive and transitive relations, a relation like this, we define the corresponding small category. I'll remind in a while what it is. Define the small category. The category is small when its objects constitute a set. So the small category I try to use the calligraphic font, and I write nothing else here because the partial order is a part of the category. So its objects are the elements of the set. However, we use the duplicated notations, and for any objects or elements, the morphism of this category from I to J is some one element set. I just denote it by star, having no natural notations for it. Perhaps I better take it in the braces to stress that it is a one element set. So it happens if I is smaller than or equal to J and empty otherwise. I haven't written the general picture of a category. I had to do it before. So if this is an arbitrary category, well, the arrows are the main heroes of the category, language and psychology, and well, all the morphisms are imagined like this. And in particular, if we have the partial order, well, you can just remember that the actual structure of this category, of such a category, is a directed graph. This construction could seem quite artificial I erase the picture, quite artificial, but we are going to apply it to the partially ordered set. Apply it to the partially ordered set of open sets of X, and the relation of being a subset as a partial order. So to get a category, now please follow the fonts. Here we try to, apply to this and get the small category that we denote by the same letters, but I'm doing my best to write them in the calligraphic font. So for any topological space, we associate the small category of its open sets. Then the long definition here turns into the following one. Then the presheaf sheaf C of commutative rings is nothing but a functor, cofunctor. So there are two kind of terminologies. The longer one, contra variant functor, and the shorter one, cofunctor, to which I'm going to stick. And cofunctor is just a functor from the inverse category that is usually denoted by the letters op that are not very easy. In my mind, it is not very easy to read them. So let's introduce this rounded minus as a character for the opposite category. I just remind, if somebody here needs it, that the opposite category is the category with the same objects and all the arrows reversed. So the presheaf is nothing but a cofunctor from the category of open sets to N, to the category of rings or sets or abelian groups. Sorry, I'd like to use the obvious name. Instead of the name of this category, we could use the category of sets, the category not yet introduced of abelian groups, and so on. So this was the example of the concept that is going to be useful by itself. And again, we are going to generalize it, the category of open sets, in our more general considerations. Is not going to be small anymore, and such formulation just cries out for some generalization. And the other piece of generalization is mentioned here. We could consider the presheafs of whatever we like. But up to now, this is just a language gaining of using category approach. Notationally, we are beyond the set theoretical mathematics. However, mathematically we are not, because the same can be written down longer in an equivalent way with more notations. Any questions about that? Well, and now we are going to consider another central object where we are going mathematically to leave the set theoretical setting, to go beyond the set theoretical setting. Well, this is our true goal, but since our course is basically related to algebraic geometry, we use the chance to discuss the foundational issues. So, maybe as an aside, we just ask what are the objects or objectives, the technical term, so algebraic, so we formulate a question, the algebraic geometry studies what? And in different times, people gave different answer to these questions. I'm going to select three of them, and for one out of these three, though it is going to be the most elementary, perhaps it is situated beyond the set theoretical mathematics. So the first approach, the most ancient one, is varieties. Broadly understood, the sets of solutions of polynomial equations, usually they are understood as embedded ones in different times in the plane, in the complex plane, in the projective sets over arbitrary fields, and so on. Of course, this is the here the objects are just subsets of some standard sets, and this approach fits to the set theoretical mathematics perfectly. Well, the next step is that of schemes. And they are just, sorry, I haven't given the definition of topological space together with the sheaf of rings. Sorry, sheaf is a good presheaf. I'm not going to list the details now. The scheme is just a pair, say X and OX, of course, not at all well, but I mentioned for somebody for those who know what I'm speaking about. So locally, structured as well some U, some Zariski open, well, some spectrum of a commutative ring and the corresponding canonically defined sheaf of rings. These schemes were introduced by Grotendika and first called pre-schemes, admit lots of further restrictions, and under the strongest of them we get back to the concept of varieties, with the main difference that is quite important ideologically, that such an object, such a scheme, is considered intrinsically considered by itself, not embedded anywhere. And the third one I'm going to mention now is the functor of points that I want to discuss just by an example. And we are going to discuss the baby question. What is... It is not quite clear whether I write down this circle or a circle. One has to choose. I mean, is a circle a name of a unique algebra geometric objects, or there are several circles? I'm going to give an answer that is in between. And we start just with the equation, and we might say that the circle is something defined by the simplest non-linear equation, simplest equation of algebraic curve. Let's give the name to this equation. Just the circle is this name. So it is an algebraic equation with integer coefficients, and there is no restrictions at all. But the question is, what solutions, where are we going to look for the solutions? and we denoted it in some natural way. For example, consider perhaps the most ancient and one of the most interesting sets. So, start with not so ancient one, but the one where we can grow. So when we think, when we switch on our intuition related to the word circle, we produce such an image. That is nothing but the set of real points of the circle. Sorry for saying what might seem trivialities. I think in a couple of steps they will be not so. So what people were really interested from the ancient times is the set of rational points on it, or the set of Pythagorean triples, like I'm writing down, and well, another one is here. Well, and the oldest document we have in the history of mathematics allows us to suppose that our ancient colleagues knew how to find, knew that this set is in fact infinite, and is one of the first document dated like this, about 1800 years before Christ. So they were studied, and well, the long lists of rational points of over rational numbers were found by Babylonian mathematicians. Now, independently of this, we can study the set of the circle over finite fields. It is a finite set, and studying it is a nice mathematical problem. Perhaps what do I say about it? Perhaps I leave it this, or maybe just say that it is related to the quadratic reciprocity. So we have just chosen the most popular fields here. Besides them, we could consider, for example, any commutative ring. So what is the functor of points? It is, well, the intermediate definition would be as follows. Again, I use some random notation for just the system of polynomial equations. Write like this: p sub 1, 0, p sub m, 0, where all the polynomials sit in the polynomial ring in the fixed set of variables. Now I erase the story about the circle because I'm just going to replace it by a more general construction. To the best of my knowledge, it has no standard notation, so we consider it, we call it the functor of points, but first of all, it is a functor. Let's call it just points, functor of points, denoted by a system, and it is a functor from the category of commutative rings to the category of sets that associate to a ring A, duplicate it like this, to a ring A, it associates the set of solutions of the system in, well, there are two versions perhaps. Well, I just say, let's write it like this, with x sub 1, x sub n in A. It is a true, just one. We use just one brace. So this is obviously a functor. Whenever we have, so obviously, let's write some details. Obviously, for morphism alpha from a ring A, a commutative ring A, to a commutative ring B, the map of sets, I use the standard notation lower star in case when the functor itself is clear like this. So it should be a map of sets. How we have denoted it in a long way. Points of A to points of B. So it is a mapping just of set, the obvious one. The solutions are substituted from one ring to another just by the application of ring homomorphism. And what we have got is belongs to a large class of objects instead to any pair of categories we are going to consider. We can associate functors from one to another. Note, I'm not saying about set of functors. It is something usually larger than set, but they deserve the study, and there is a special part of category theory that studies the set-valued functors. So, for the time being, we know a large class of set-valued functors. That is, we know that any sheaf of presheaf of sets define the set-valued functor, though on some special kind of categories, category of open sets on the on an arbitrary topological space. And here I can just state an important and largely open problem that is of the abstract characterization of the functions like this, the functors like this among, writing among in brackets just because it is not a subset, but something else among other functors. Let me give an obvious property of this class of functors that is by no means exhaustive. So one of the properties is that it says finite object to finite ones. We can even restrict ourselves to finite fields, and the question of the cardinalities of the system of solutions over finite fields was one of the central questions of mathematics of the 20th century. However, it did not produce the exhaustive answer to this question. I mean, there are certain other nice properties that select the functor of points among all the functors. And this problem is, I think, interesting and, well, proper for young mathematicians by itself. But in our course, it shows clearly the kind of mathematics where the set theoretical approach is insufficient. You can take a certain field and study the system of equations over this field, but it is just something like a value of a function in just one point. What is really interesting is the whole functorial behavior. So here my plan of explaining why mathematicians tend to move beyond set theoretical mathematics is over. Any questions about this part? And I can just begin the next topics. Any questions from?
Question. Why rings A and B union quotient ring of Z of X i's by ideal generated by P i's, yes?
Say it again, please.
By rings, these rings, maybe I didn't understand the definition of Functor of Points, yes? By rings in this, yes, by rings A and B you mean some quotient rings of rings of polynomials by ideals?
No algebraic operations are meant here. The question is really delicate because here I'm using only the standard notations, but x's here are names of variables. To tell the truth, they mean nothing. They are just define the rules of multiplication of tuples of coefficients. But here the same x's are just the sets of elements of the ring that we can substitute to the system of polynomial equation in the most naive way. Other questions? Okay, then. Well, my second planned part was the categorical language. However, I think that I have used the most part of non-standard notations, and since they didn't cause questions, perhaps we can proceed with that. However, what we are going to define is some class, maybe the most important class of categories, the so-called concrete categories. Here the explanation in words is much easier than the formal definition. The concrete categories are just categories of sets with some additional structures and morphisms that respect these structures. Maybe it is not a mathematical definition, maybe it is, because I've never met the situation when two people understood differently the meaning of the respect to the structures. However, we give, after this clear, I hope, clear explanation, I give a formal definition. So it is a category supplied with the forgetful functor So we denote it in a long way as functor for get. So it is a category together with the forgetful functor from C to set here, but there will be a different forgetful functor, so it is functor from C to set. So the faithful, I'll remind what it is. Faithful functor, that means injective on morphisms. And we now we are going to fix several categories, the names of some of which we have already used. I try to use more or less standard names, though it's impossible, they are not completely standardized. So that tautologically it is the category set. Now the category of groups, usually it is written down in the abbreviated way. So let's say a word about the forgetful functor. This functor associates to a group its set. The faithfulness means that the morphism of group turns into the mapping of sets in the most obvious way. So the other categories are groups. So ring, the category ring of rings is not the category of not necessary. Commutative. Now I use an informal sign that of course deserves some discussion, and maybe we do it, but not today. I mean the concept of subcategory. Here is the category we have used. Commutative, the category of commutative rings. And here again we have the abbreviated category of fields. We could consider also the subcategory here of division algebras, but there is a terminology problems in different languages. They use different terms. In English it is skew fields, in Russian and French tela corp. In German also, but I'm unable to pronounce it. However, I don't think we are going to meet them. So this is perhaps the most important algebraic categories. So the structure constitute just the set, one operation or set of operations, and the morphisms are obvious. And among others, we just perhaps mention the category also mentioned of topological spaces, and of course continuous mappings that have to be defined. Perhaps I'd like to stress that the definition of the morphism of topological space is not so obvious as with the algebraic categories. More than that, there is quite a reasonable, so the the additional structure is defined just as well, set of open subsets, and one could think that the respect to this structure is mapping open subsets to open subsets, and this is an important class of mappings of topological space, both in classical topology and in Zariski topology, but they are usually considered together with the assumption of the continuity. So this definition of morphisms in terms of pre-images of open sets is maybe not so obvious as it could seem. So these are concrete categories, but let's recall ourselves that there are not concrete as well. As for categories, we have discussed in relation with coverings and sheaves. We'll continue it, but now we are discussing maybe more basic categories, and the one we have discussed, just let me reproduce the symbol, the small category I constructed from a partially ordered set. And there is another very important category. I could say that it is the most important for the construction of any kind of homological theories. It is the category of topological spaces, but with the morphisms in the category, homotopic category. It is read like this: from X to Y are not the sets of continuous maps. Let's write them down here. The continuous morphisms are morphisms in the category top, but instead the homotopic classes of continuous maps are considered. So the result is like this. By the way, these are the final words of today's lecture. The great advantage of this set of morphisms, that is the homotopy classes of morphism instead of all the sets of continuous function, is lies in the fact that it is small. Usually it is quite a small set, and one might think that they are easy to study. However, the set of homotopic classes of the mappings of between spheres these sets are widely open. Perhaps I would put a question mark and an exclamation mark, because these sets, called the homotopy groups of spheres, by the way, they are abelian groups of finite type, all of them are, they were very intensively studied in 20th century. I have a feeling that not so intensively they are studied now, but still many questions about the table is not complete. So it is again just an aside remark that perhaps reminds us that well, sometimes defining the natural categorical construction leads us to natural and interesting mathematical problems. This is one of the example. So we'll freely use the names of this category in the same, if somebody is going to forget them, of course, I will remind, in the same way as we are using the names for world constant, natural numbers, integers, well, rational numbers, and p-adics, and so on. So our time for today's lecture is over. However, any questions from the physically present people or from distant participants? Okay, then thank you for your attention.